Water. This simple molecule, composed of 2 hydrogen atoms and 1 oxygen atom, is crucial for all known life. It sustains us, shapes our planet, and holds the key to understanding the vast cosmos. But what if I told you that water is not unique to Earth? That it exists in abundance beyond our pale blue dot, hidden in the darkest corners of space? The discovery of water in space has revolutionized our understanding of the universe. It hints at the possibility of other life-bearing worlds and has profound implications for the future of space exploration. Join me on this journey as we delve into the fascinating realm of water in space, exploring its origins, its presence in our solar system, and the tantalizing possibilities it holds for the future. The search for water in space is a search for life itself. It is a quest to understand our place in the universe and to unravel the mysteries of our cosmic origins. So buckle up, fellow space explorers, as we embark on this thrilling adventure to explore the oceans beyond Earth. Where did all this water come from? It's a question that has fascinated scientists and philosophers alike for centuries. Water, the essence of life, covers more than 70% of our planet's surface and is crucial for all known forms of life. But its origins are far more ancient and cosmic than one might imagine. How did this life-giving elixir come to be so abundant in the vast expanse of space? To understand this, we need to embark on a journey that takes us beyond our planet, beyond our solar system, and into the very fabric of the universe itself. To answer these questions, we must travel back billions of years to the birth of the universe itself. Imagine a time when the universe was in its infancy, a mere fraction of a second old, and everything we know was compressed into an incredibly hot and dense point. In the aftermath of the Big Bang, the universe was a chaotic soup of elementary particles. These particles, the fundamental building blocks of matter, were in a state of constant motion and interaction, creating a seething, turbulent environment. As the universe cooled, these particles began to combine, forming the first atoms, hydrogen and helium. This cooling process was crucial, as it allowed the universe to transition from a hot, dense state to a more stable and structured one. These atoms, the building blocks of everything we see around us, would eventually give rise to stars and galaxies. The formation of these celestial bodies marked the beginning of a new era in the universe's history, one where complex structures could emerge. Within the fiery hearts of stars, hydrogen atoms fused to form helium, releasing enormous amounts of energy. This process, known as nuclear fusion, is the engine that powers the stars, providing the light and heat that we see from Earth. This process, known as nuclear fusion, is the engine that powers the stars. But the story doesn't end there. As stars continue to burn their hydrogen fuel, they create heavier and heavier elements in their cores through a series of fusion reactions. As stars age and exhaust their fuel, they begin to produce heavier elements, including oxygen. This process of element formation is known as nucleosynthesis, and it is responsible for creating many of the elements that make up our world. When massive stars die in spectacular supernova explosions, they spew these newly formed elements into space. These explosions are among the most energetic events in the universe, capable of outshining entire galaxies for a brief period. Among these elements are the ingredients for water, hydrogen, and oxygen. These elements, scattered across the cosmos by supernovae, eventually find their way into interstellar clouds, where they can combine to form water molecules. Over eons, these atoms collided and combined in the vast interstellar clouds, forming molecules of water ice. These icy grains can be found throughout the universe, in the cold, dark regions of space where stars and planets are born. This cosmic dance of creation is happening even now, ensuring a continuous supply of water in the universe, from the birth of the first atoms to the formation of water molecules in interstellar space. The story of water is a testament to the incredible processes that shape our universe. Our solar system is teeming with water, hidden in plain sight. This revelation has transformed our understanding of the cosmos and the potential for life beyond Earth. While Earth is the only planet we know of with liquid water on its surface, it is not the only place where water exists. Water in various forms is scattered throughout our solar system, from the inner planets to the distant reaches of the Kuiper Belt. Our celestial neighbors harbor vast reserves of this precious resource, often in unexpected forms. From ice-covered moons to vapor plumes, the presence of water is a common thread that links many of these distant worlds. One of the most promising places to find water in our solar system is Europa, a moon of Jupiter. Europa's surface is a thick shell of ice, but beneath this frozen crust lies a vast hidden ocean. Covered in a thick, icy shell, Europa is believed to harbor a subsurface ocean that may contain more water than all the oceans on Earth combined. This ocean is kept liquid by the heat generated from tidal forces as Europa orbits Jupiter. Data from NASA's Galileo spacecraft suggests that this ocean is salty and may be heated by tidal forces from Jupiter, making it a prime candidate for life. The potential for hydrothermal vents on the ocean floor could provide the necessary conditions for microbial life to thrive. Another intriguing target is Enceladus, a moon of Saturn. Despite its small size, Enceladus has captured the imagination of scientists and the public alike. This small, icy world surprised scientists when the Cassini spacecraft observed plumes of water vapor erupting from its south polar region. These plumes are not just water vapor, they contain a mix of organic molecules, salts, and other compounds. These geysers originate from a subsurface ocean similar to Europa's, and contain organic molecules, hinting at the possibility of life. The discovery of these plumes has led to a surge of interest in Enceladus as a potential habitat for extraterrestrial life. Even our own moon, once thought to be dry and barren, has revealed surprising secrets. The discovery of water on the moon has profound implications for our understanding of its history and its potential for future exploration. Observations from NASA's Lunar Reconnaissance Orbiter and other missions have confirmed the presence of water ice in permanently shadowed craters at the lunar poles. These craters, which never see sunlight, have preserved water ice for billions of years. This discovery has significant implications for future lunar exploration, as it could provide a valuable resource for astronauts. Water on the moon could be used for drinking, growing food, and even producing rocket fuel, making long-term lunar missions more feasible. As we continue to explore our solar system, the search for water remains a key focus, driving our quest to understand the potential for life beyond Earth. While icy moons like Europa and Enceladus hold vast reserves of water, they are not the only celestial bodies that harbor this precious resource. These moons, with their thick icy crusts and subsurface oceans, have long fascinated scientists and space enthusiasts alike. The discovery of water on these moons has profound implications for the possibility of life beyond Earth. But the story of water in our solar system doesn't end there. Water is not confined to these icy moons. It is a widespread and essential component of many celestial bodies. From the distant reaches of the Kuiper Belt to the inner regions of the asteroid belt, water can be found in various forms and locations. This widespread presence of water suggests that it played a crucial role in the formation and evolution of our solar system. Comets, often referred to as dirty snowballs, are composed of ice, dust, and rock. These ancient travelers are remnants from the early solar system, preserving the primordial materials from which the planets and other celestial bodies formed. The study of comets provides valuable insights into the conditions and processes that prevailed in the early solar system. As comets approach the sun, they heat up, causing the ice to sublimate, transition directly from a solid to a gas, creating a glowing coma and a characteristic tail. This process not only makes comets spectacular objects to observe but also releases water and other volatile compounds into space. These materials can then be captured by planets and moons, contributing to their water inventories. The sublimation of cometary ice is a dynamic and fascinating process. As the comet's nucleus heats up, jets of gas and dust erupt from its surface, creating a bright and expansive coma. The solar wind and radiation pressure then shape this material into the iconic tails that can stretch for millions of kilometers. These tails are not just beautiful to look at, they are also a testament to the complex interactions between comets and their environment. These celestial wanderers have been delivering water to Earth and other planets throughout the history of our solar system. The impacts of comets and their fragments have likely played a significant role in shaping the surfaces and atmospheres of planets and moons. By studying these impacts, scientists can learn more about the history of water in our solar system and the potential for life elsewhere. Asteroids, rocky remnants from the early solar system, can also contain water. These bodies, which range in size from tiny pebbles to massive objects hundreds of kilometers across, are found primarily in the asteroid belt between Mars and Jupiter. While many asteroids are composed of dry rocky material, some contain significant amounts of water ice. While most asteroids are dry, the discovery of water ice on some of them has opened up new possibilities for space exploration and resource utilization. These water-bearing asteroids could serve as way stations for future missions, providing essential resources for astronauts and spacecraft. Some asteroids, particularly those located in the outer regions of the asteroid belt, contain water ice. These icy asteroids are thought to have formed in the colder regions of the solar system, where water could condense and be incorporated into their structures. The presence of water ice on these asteroids suggests that they could be valuable targets for future exploration and mining efforts. These water-rich asteroids could potentially be valuable resources for future space missions, providing water for astronauts and fuel for spacecraft. The ability to extract and utilize water from asteroids could significantly reduce the cost and complexity of long-duration space missions, making it easier to explore and colonize other parts of the solar system. Providing water for astronauts and fuel for spacecraft is just one of the many potential benefits of asteroid mining. Water can be split into hydrogen and oxygen, which can be used as rocket propellant. This capability could enable more ambitious missions, such as crewed missions to Mars and beyond, by providing a reliable and accessible source of fuel in space. These discoveries highlight the fact that water is more common in our solar system than we once thought. The presence of water on comets, asteroids, and other celestial bodies challenges our understanding of the distribution and abundance of this vital resource. It also raises intriguing questions about the potential for life elsewhere in the solar system. It is not limited to planets and moons but can be found in a variety of celestial objects, even those that seem unlikely at first glance. The search for water in our solar system is an ongoing and exciting endeavor, with new discoveries being made all the time. Each new finding brings us closer to understanding the origins and evolution of water in our cosmic neighborhood, even those that seem unlikely at first glance. The presence of water in such diverse and unexpected locations underscores the importance of continued exploration and study. As we venture further into space, the knowledge we gain about water and its distribution will be crucial for the future of space exploration and the search for life beyond Earth.